Hello and welcome to another Würth Elektronik webinar. My name is Torolf Schwan and I will moderate the webinar today. We are very pleased that you took the time to participate in our webinar. Our speaker today is our product manager Loran Völkel. He will hold today's webinar on how do I solve EMI problems on PCB level and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. If we are unable to answer all your questions within these 15 minutes, please email us at isos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. The link to the recording of today's webinar as well as the presentation will be sent to you in a separate email one day after the webinar. You can also watch the recording of today's webinar a day later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I will hand over to our speaker Loran Völkel and I wish you an exciting webinar.
Hello everybody, my name is Loran Völkel. I'm at Würth Elektronik, Business Development Manager and Field Application Engineer for different EMI solution and also for power supplies. Today in this small talk or small webinar, I want to show you some idea how to solve EMI situation on PCB level. First of all, when you are talking about EMC, well, you have to require and to fulfill some different directives. So when you put something to the European market and you want to sell this device, it must be compliant with this CE compliance. And the CE marking, it's different depends on your device. If it's a low voltage device or you have a radio module inside or RF module, which is communicate. In the RED, it is already the EMC compliance already. It is automatically inside. The machine directive for the industrial machines are also including the EMC requirement. So we have different directives which are right now only valid the 2014 law. You have to take care if you still use the law from 2004 or 2008, they are not anymore valid. Please consult your EMC lab when you are doing a declaration, else you are already not compliant. If you sell anything to outside of Europe, you must be, like in USA, you must be FCC compliant. The FCC is a little bit different from a European compliance because they don't care about immunity test, but they are very, very strict for emission. If you sell something to Japan, you have to be VCCI. Australia have the CTIC. If you sell something to China, you must be CCC compliant. You will see that every civilized country has EMC regulation. Well, it's very important also of economical point of view when you start to think about EMC, because I saw many times the customer when they go to the EMC lab, that's the time when they start to think on EMC. But this is almost too late and this is very expensive to do a redesign or to make a modification on anything because it's almost too late. My opinion is that the EMC thinking, the design of the EMC, it starts already in very early stage in development during you make your schematic. when you know that you have a very high rise time of some signal, or you have high currents, or your switching frequency, you know your switching frequency of your DC-DC converter, you should take care about what happened with the harmonics, which kind of filter I have to design to this switching device, because it will happen that sometimes in EMC it is because you're just not thinking about the harmonics, or because you're not thinking that you will need a filter anyhow, or you want to save just the money for the filter, and you put a very expensive solution outside of the box with some snap-on ferrites, or you have to modify your completely shielding. Actually, the EMC is starting quite very early, and if you make the place for a 0 ohm resistor by the VCC on every IC, and you leave a pad free for a capacitor, and you go to EMC lab, you just desolder the 0 ohm resistor, and you can try a chip bit ferrite. If you had prepared a pad for a capacitor, you just can solder a capacitor. Many people say we don't have space. Okay, there's always a way. 0201 size, maybe it's difficult to solder by hand, but sometimes it's space for 0603, or even some people can solder by hand 0204, but I would definitely go by 0603 or 0805. Now, how you can check the EMC? This is the most important question as well, because most time you think, okay, I have a scope at 250 megahertz, but I have to fulfill a requirement in EMC until 1 gigahertz. You cannot see with a 250 megahertz bandwidth of scope on 1 gigahertz signal. So you have to put at least some money for investment in the scope. If you want to hunt 1 gigahertz, you need 3 times higher bandwidth. So you will need a 3 gigahertz bandwidth as well. With a 250 megahertz, it will be impossible to see that. But much better is, of course, if you have money for investment and you can investigate that when you are set up, I would say, pre-compliant measurement, like a anechoic chamber, EMI receiver, some antennas. The problem is that it's very expensive. Anechoic chamber for 200,000 euro, not everybody can have this budget. EMI receiver, if you want to have a good one, between 40 and 60,000 euro, it will be very difficult to find one. But investment for a spectrum analyzer, which can go up to 3 gigahertz, that will be possible to pay. This is not so expensive, and there are some manufacturer which you can buy quite very cheap. But only with the scope, it's quite difficult. I would suggest buy a spectrum analyzer, have some near field probes for electrical field, for magnetic field, and then you can start to investigate and start to find out where are the EMC noise source, and then fix it, and then go just for qualifying in the EMC lab. Now, also depends on the different system impedance, which kind of filter topologies you have to use, because you can't use always just a capacitor and put more and more capacitor, because that will be not always a solution. I always start to filter if I found out this is a differential mode noise. I start with my LC filter. If I see that LC filter is not giving enough power, not giving my expected result, then I give to the LC filter a second C. So I did build my P filter. With the P filter, I play with the capacitors. And when I see, the capacitor doesn't have this real big impact, so I go back to my LC and I try to play with the two different inductors. So I have my T filter. One of those filters will have a massive impression insertion loss, and you will find the right solution just by, if you don't know exactly the system impedances, which is mostly the problem. It's not like in a university where everything is 50 ohm. In the real life, you will find out that the system impedances is a very, very rare 50 ohm. For this reason, I suggest to use small capacity, maximum 1 microfarad, use low ASL, low ESR, and for the inductor, please take care that you use low Q factor inductance. Use chokes. You know, the quality factor of inductor um, is not this time difference between made in Germany or made somewhere else. It is depends what is the report of impedance reactance to the R losses. This is the definition of the Q factor. The problem is that the Q factor is not included in the formula, and most people will forget or will deny to think about what is the Q factor. Please be aware about this Q factor, which is crucial for your filter, because the Q factor for inductance in a filter must be very low. If it's too high Q factor, it may ring your filter. Your filter start to increase the amplitude or multiply the noise peaks and will not be a filter. Be aware also about the self-resonant frequency of the capacitor and inductance. They should be not very close to each other because you don't want to build oscillators. Now, where are the EMI noise sources? Because you want to know who's responsible for this noise, who make that noise. First of all, I will say, let me check a little bit what happened with the buck converter. A very simple buck converter, take the current on input, not continuously like a resistor. He will switch off and switch on. It means it will generate automatically on the input with his ripple a conductor emission. At the same time, because the output, it is not a continuous voltage, because you discharge and charge a inductance and a capacitance, you may have also some rest ripple, which can generate again some conductor emissions. But the most dangerous, what you are doing, look what is happening here. First of all, you have an input capacitor. With the input capacitor, you charge this energy in input capacity, then transfer to the switch into this inductor and to this output capacity. If you are radio amateur, you know that two capacitor inductance and another capacity, it means this is your dipole antenna. Actually, you have taken care a lot of this track of input capacity, maybe even the diode and the output capacity. This track here, this PCB track, if you take a near field probe and you go close to this track, you will find out that this is the most radiating and most dangerous EMI track. Please, because of this reason, don't push the auto routing button. If I would be the manufacturer or the programmer of this software, I would rename the button to make EMC problem button. Don't push this auto routing button. Please take care that this track is short as possible, low impedance as possible, because this is your major radiation point in the anechoic chamber. As soon you keep this antenna small as possible, this is very welcome. And think about 1 millimeter PCB track is exactly 1 nanohenry. So perfect inductance. Additional, you have to take care about these DI/DT loops, because you have here on a different noise loops, you have an input, a noise loop, you have on output noise, but depends on the on his switching mode. You have to take care about this different consider this different noise path, where he can be through the input capacity out to the output capacity, or just between the inductor and the output capacity. So you have to think about, in the buck converter, you have an input of quite very noisy area. This is what you have to filter. In a boost converter, you have to filter more the output. The boost converter is not so aggressive on input, but is very aggressive, very noisy on the output path. So this is the two area where you have to think about this area. And of course, you have also some parasitics, because the capacity is not the ideal capacity. The PCB track and all this input line is not the ideal. So you may have here a quite big noise on the input, especially by the buck converter. So if you know the parasitics of our input capacity, like the ASL value, the ASL value, if we know all the parasitic on the line, which is going to this capacity, already you can really with a simple formula, you can already know what is the expected voltage of the noise if you know all these different parasitics. Additional, you think that you have a digital, very nice, ideal rectangle signal on your switch. Well, you may see on a scope that is overshoot and ringing a little bit. This high frequency ringing and overshoot, and especially in this area where you have a switching frequency 250 kilohertz, and you see at 500 megahertz some noise, and you think, where the hell is coming that? It is because also the diode is not the ideal component. It has also parasitics. And in a very high frequency, you may have here a very high frequency resonance circuit. How to avoid that? It's quite simple method to use here instead of diode, to use a synchronous buck where you have two MOSFETs and you emulate a diode. With this one, you may have a little bit less ringing and you may have a little bit less overshoot. But the best thing is always to keep the diode or MOSFET and the output capacity, including the storage inductance, short way possible. If you get this area short way possible and you don't build big long antennas, it may help for as well. Additional, you have to think about the PCB tracks, how you track your PCB, because if you have a controller and you have an output MOSFET, you have to think about the back path. The back path from this signal, you have a digital signal actually, you have a rectangle digital signal, even it's not a data, but it has the on-off to the MOSFET. You have to take care, where is this current coming back to my controller? So give the possibility to this current to come back on the shortest way. And the best thing that you can do, make kind of PCB track matching, antenna matching on PCB level, that you have the same length and the same distance to have the same impedance between MOSFET and the controller. Then you can do a good thing. I like to do that in two layers, like I put on the top layer from controller to the MOSFET, and the bottom layer I make additional path, additional, not just by accident where the current come back, I make a direct path back to the controller from the MOSFET to be sure that this digital signal are running on in this way. And then almost you have less problem, especially for high frequencies. Now, how to design a good filter? Well, the most simple filter, you have the input capacity. You can put on front of the input capacity a very simple choke. This inductance, you have to be aware that he cannot be several millihenry, because if he's millihenry, this input capacity will die hungry because it will be not charged in time. So it must be correlated, the input capacity value, to the input filter inductance. Normally, you have a filter value for the inductance between something by 2.5 microhenry, maximum 47 microhenry. Very, very rare you will need a higher inductance, but then you have to take care about this capacity that he will be not charged in time. So the capacity value must be adequate, because inductance, they slow down the current flow. This filter is for differential noise. So if you think about this inductance value, you can try, like I told you, between 2.5 microhenry in until 47. But a good starting point, I always start with 10 microhenry, and then I see, okay, I need a little bit more filtering, then I go up to 22, or if I have a high frequency issue, maybe the resonant point is already reached, so I go down to 4.7 and try in this way. How to calculate the rated current to this inductance, and which important issue it is that you have to take care that through this input current, input inductor, it will flow a quite high current, not the same current what you have on the output. I have here an example like a 5-volt output and 4 amp with a 20-volt input. I will say I will need efficiency minimum 80%. If I make this input current, for my example, I will need an inductor at 1.25 amp. It means my inductor at 1.25 amp, you have to take care that this inductor should be not saturated. It should be in a linear area. If you look to the inductance versus current curve, this inductance value must be stable at 1.25 and not already 30 or 50% saturated. Because if you have a DC premagnetization, the filter won't work correctly. Myself, I've always multiplied that by 2, and then I'm almost on the safe area. The DC resistance will be less, and my efficiency will not suffer because of my filtering. Okay, if sometimes the size too big because of the currents, you have to take a compromise and go down, but never ever go less than 80% efficiency, because, you know, if you build something today which is less than 80% efficient, save the money for the switching, take a big resistor and burn the energy away. So 80% minimum, this is for today, a minimum request. I know many companies, they don't do anything, they don't admit anything below 90% efficiency for a DC-DC converter. But come on, 80% is easy going today. If you want to do something better, you can put additional to the inductor. You can add a ceramic capacity of value 220 pico, maximum 1 nano, very low ASL. You can take a multilayer ceramic one and add a chip with ferrite additional in row. You build like a P filter, a T filter, sorry, T filter. But this ferrite bit, you should not use the super duper 2.2 kilo ohm one, the most powerful, or 2.7 kilo ohm. It makes no sense. All these 2 kilo ohm ferrites have a peak 2 kilo ohm, but because of the multi-layer, have many layer inside, and he will not have the nice bandwidth. Additional, all the ferrites are measured in a 50 ohm system impedance. We don't have 50 ohm system impedance at DC-DC converter. We may have something between 10 and 20 ohm system impedance. In this area, if you put a 100 ohm, maximum 300 ohm ferrite bit, you will be much more happy, because you will have, with less layer capacitance, automatically a much better bandwidth. You will cover much more frequency, and the efficiency will be good enough. A 2 kilo ohm make no sense, because it's have a 2 kilo ohm but very narrow bandwidth efficiency. All that only because of differential mode noise. Now, this is a buck converter. If you have a boost converter, you have just to mirror exactly that what I show you on a buck converter. You can mirror exactly to the output at boost converter. Boost converter should be filtered on output, because they have a quite massive ripple, and they are almost not so noisy on input. If you build a buck boost converter, well, this is bad luck. You have to put something on input because you have a buck mode, and when you have a boost mode, you have to put something in the output. And especially when you put input and output filter, take care about the DC resistance of the inductance, take care about DC resistance of the ferrite. Even if you don't have 10 amp, you should use a 10 amp one, because they milliohm resistance, it won't destroy your efficiency. Now, if you have something like a common mode noise, well, all this ferrite bit and inductor won't help enough. You have to use a common mode choke as well. But be aware, if you use a common mode choke, you can put on front of common mode choke the minus to ground plane. You go to the common mode choke, and you put after the common mode choke again to the ground plane, because then you make a short circuit of this winding. And beginning from this point, the common mode choke is just a heavy component on your PCB. It's good for the kilo, but it's not good for the EMI. You go inside of the PCB with the common mode choke, and after the common mode choke, you declare this is your own clean ground. He has a galvanic connection to the output, but only through the coil. Everybody in your device must talk to this leg of the common mode choke. It means to his pin, it means the same ground point. You can make a star distribution, but take care that no IO are allowed that makes any connection around the common mode choke. He must be from the common mode choke taking a ground, because else he will have a not a current compensation, and he will be not effective. This is good for common mode noise. How to make the layout? Well, I will say this is crucial because you can make a best calculation of the filter. You can take the most expensive components what you can put on the PCB. But if you make a wrong PCB layout routing, you will destroy all the effects of the best components. In my previous job, I was also design engineer and I did not make my own PCB design. I have somebody, a colleague who did make, it was a girl, and you know, girls like to put everything in kind of in a very nice, organized. Resistor in one row, capacitors in one row, inductors in one row. So according to the schematic, this T filter was correct connected, but that was not so good for the noise. If you, especially if you have a blocking capacity and you make a long track to this ground, it is not the best solution anyway. Please consider that a capacitor, if you make a filtering capacitor, after the pad, you put directly the wire to the ground. One single wire, it has already 0.5 nanohenry inductance. So if you have the possibility to put two wires, it's like two resistors in parallel, two inductance in parallel, and make your capacity more efficient. Now, if you have this V insertion above high frequency, well, you need that to do only if you want to filter gigahertz. If you don't want to filter gigahertz, you don't need to do that. I know it's very difficult to draw this by each design, but because of this reason, I would recommend if you don't want to filter gigahertz, you don't need to do this. Okay, no, that was one click too fast. So this is an experience which was given from a customer. Customer did go to the EMC lab. He failed. He asked for support. We helped him somehow. We was with him in the lab, and because he failed, we find the solution. We put by air PCB. So we soldered directly to the connector, two capacitors, and we soldered additional common mode choke. And we found out, hey, with this solution, he will pass the EMC test. Okay, so his homework was now go home, solder this, make a PCB solution of this in-air soldered components. But we tell him, please don't modify too much on the PCB. Just push a little bit, make a little bit space to fit these additional three components on the PCB and make them close as possible to connector. Well, he pushed away a PCB and he put this common mode choke and these two capacitors as well. And finally, he goes back to the EMC with his new redesign number one, and he failed again. Then he come back to us and say, "Hey, Laurent, I don't know why EMC test was again bad. I failed, and it was better like first time, but anyhow I failed again." And I was like, "What?" We was together. We found out that it was a good solution. Why you fail again? I asked him, maybe you did not use Würth Electronic components. He said, no problem. I use your components. This is for sure. So I was sure that the components was good. And I say, let me see the schematic. I saw on the schematic, he placed the components the right way. But then I asked, let me see the PCB. Can you send me a PCB that I make my own measurement? As soon as I have this desk on my desk, the PCB, I saw what this guy did done. You have the noisy area on this pad. You try to filter him, you put a common choke, but after the common mode choke in the filtered area, you couple back the noise. If I would not see it with my own eyes that this is so important, I would not believe it. So I tell them, please, can you go to this common mode choke one side in and one side out? Redesign number two. One side in, one side out. With this one, I saw already the PCB, the Gerber file. He sent me the Gerber file. I said, no, please pay attention. This is also dangerous zone. This is again can happen. I don't know. It's electrical magnetic field, but can contaminate again because it's too close to each other. Consider a common mode choke like a transformer, which is galvanic connected. You have the noisy area, the dirty area, and you have the clean filtered area. With the redesign number 3, here you can see capacitors and the common mode choke and the exit. With this one, he passed the EMC test, and he was happy. If I would not see this first design, I would not believe that such small PCB, I would say wrong PCB routing could make such crucial effect that you're not talking about 2-3 dB, you're talking about 15 to 20 dB difference. So please be aware, if you filter something, to not cross or not be too close to the cleaned and filtered area. What is the big importance between shielded and unshielded inductance? Because I always recommend use a shielded inductance for storage inductance. If you make a cut into the inductance like a non-shielded and unshielded, you can see the big magnetic field is close to the wire. The magnetic field is closing here, but actually a not shielded inductor, it means a 90-degree antenna to the PCB layer. So you make a big magnetic field because he doesn't have a quite good magnetic field closing. He has a infinite air gap. The air gap at the shielded inductance is on the top and the bottom. We need this air gap because we don't want to saturate the inductance. But if you look on this magnetic field generated by a shielded inductance, the big magnetic field, he will not take the air because air is not so good magnetic conductive. He take this way through the shield and come back, but he will have some leakage anyhow. Because of this reason, don't track anything below the inductance on the same layer because this is dangerous. You can build transformer. But this is paid back if you use shielded inductance because like here in this example, this is a 1 amp output DC-DC converter switched by 2 megahertz. And if you look just at the conductor emission, we talk about conductor emission, 150 kilohertz, 30 megahertz. If you look to these peaks, which is generate a DC-DC converter, very simple in conducted emission. And you just take a soldering iron. Don't change anything on the setup, not move even one piece of wire on the desk. Desolder the inductance from unshielded version and solder the same inductance value on the same pad, 10 microhenry shielded version. It will happen that your peak on the conductor emission will drop almost to 90 dBm better. So just because of the shielding, it will be not contaminate the system, and sometimes you can have a good solution for conductor emission. In radiated emission, I think I don't need to explain anything on this picture. In radiated emission, the inductor is the antenna which is, make a noise. And if you put the shielded version, it will be much more happier. About some examples, this is another example from a customer who got a very simple DC converter for electrical motor. He go to the EMC lab. He did not pass the test by using the conducted emissions. And when he look on this, okay, we have to do something like, to filter somehow. We saw he used two load core inductors, not shielded one. It's a dual layer PCB. We had the idea, please change these two inductors to shielded one and float on the top side with ground and make vias to have a good ground plane and try this again. He goes back to the EMC lab. The EMC lab look on his schematic number 1, schematic number 2. He asked him, where is your filter? The guy said, no, don't need filter. I put some other inductance and I make a little bit PCB redesign. The guy from the EMC lab, like a customer tell me, ask him, do you think that your PCB is now green instead of yellow? It will help to pass EMC test. The guy said, well, I'm here now. I pay for the measurement. Please measure it. After he start to measure this design, the EMC guy start to be nervous. He start to look on his machinery if his machinery is really measuring correctly, because this is the noise floor on the measurement. You can see the noise floor here, and that's what his device are doing after this redesign. It was a big impact, which nobody did expect, this lucky punch, but it makes so much fun when you see that the EMC guy start to be nervous because he doesn't believe that his machinery working very well. So this is the most satisfaction what I can tell you from my side, because normally if you go to EMC lab, you fail by first shot. It's very rare by first shot to pass the EMC test. And you can see on the smile, this sarcastic smile of the EMC guy, they say, you are 40 dB above the limit. But when you are 20, 40 dB below the limit, then they start to be nervous and they look a little bit different. And then you can make your dirty smile and say, hey man, I can do good EMC design. Well, I wish to everybody to have this satisfaction. I tell you, I had a few times, but not too often. Well, where you can get all this data, I can recommend to you go to our website online.com/RedExpert. You can have all these different inductance versus current curves where you can see if this inductance still works or not works for the filter. You can sort the inductance by choosing shielded version or a surface mount or through hole version. You can make a filter for the current which you need. Actually, you can put all your data here in the parameter where you want to know exactly which inductance value you need according to your duty cycle, according to your switching frequency. And if you put ripple current not higher like 30, 40%, you may have almost quite a good solution, good resolution. And all this data which you will find here, it is same in the data sheet, but because it's measured value, but you may have the possibility even to see what happened when you put this device at minus degree, like minus 40 degree. How much is his inductance dropping? How much his saturation move, especially in a very high hot area. You may have some inductance which is operating above 100 degrees Celsius, and that means the inductor will saturate a little bit earlier. But how earlier? No manufacturer tell you until today. In RedExpert, we have all this measured data, and you will find all this value in these graphs, and you can see, my inductance is 100 degree. Maybe it will be too early saturate. I should have all inductance which have 150 degree operating temperature, or I have to choose another one because this is too dependent of the temperature. All this value, all this calculation is not based on Steinmetz formula. It is really measured value which can be reproduced, and you will be happy when you will see that your device works at minus and plus degree. If you use a TI chip, you can go to the toolbox at our website. You click on WEBENCH and open this WEBENCH software. By the TI, you can choose with this switch after you put your input voltage, output voltage, and current. You can choose between high efficiency with this button. You can go to the smallest footprint, the smallest inductor, smallest chip, or the lowest BOM cost. Well, the switch have not a function where you can have highest efficiency, lowest cost, and smallest footprint. This is kind of paradoxon, which I would be happy to offer it to you, but as you know, you don't can't have everything in life the same in a DC-DC or in the EMC. You must make a compromise, whatever you want to know, what is your priority. For LTSpice, I recommend is still the link is working, even it's by analog device. The LTSpice is still available, and maybe in the future will change to analog.com, but still works. You can download the LTSpice. The LTSpice, I like the LTSpice because even it is now the 17 also on the market. I will I still using the LTSpice 4 is still updating. What I like in LTSpice, it is because you have a library of components with all the parasitics. You don't simulate only just ideal components. You simulate components with the ideal, not with the, it's with the parasitics value. So you will have the parasitics included in the simulation, and then you can decide by yourself, this inductance is good, this capacity is already resonant. It is better to choose the right one, because if you choose just ideal component, I don't know who will build to you. Especially by chip bit ferrites, you will find out that Würth Elektronik supply even a DC BIOS load model. You can find out if this chip bit under your operating load current is still effective, or already bye-bye is just only just a heavy product on your PCB because it's saturated. And this is in LTSpice included. More you can find in these books like LTSpice, Trilogy of Magnetics. Already the 5th edition is on the way to be printed. Trilogy of Connectors, ABC of capacitors or even this DC magic modules, please ask my colleagues which are worldwide supply to you. My sales colleagues, they will be very happy to give this book for 2-3 weeks to look on inside if you like it. If you don't like it, you just give it back, or you can keep it and you have to pay in the local currency. Okay, now let me see how many questions we get. I will open the questions on my here. Okay, we have here a question for the PCB layout recommendation. That kind of coupling value is almost PF level. It's only affect over 100 megahertz? Question mark. Or do you think it's also affect lower frequency EMC? Okay, well, the layout recommendation, if you mean this with a common mode choke, actually it is right. Normally it's not a very high uh, capacity value. It could be few picofarad, but it could be reached already nanos as well. But this is crucial if you have an electrical field. If you have a magnetic field, then you have a magnetic coupling, which is more dangerous. And the picofarad is not the crucial value. It is just because these two tracks was too close to each other. The customer had something like 5 amp, which is not so big current, but is still enough to just couple through and to have this effect. So it's always not only just to think it is electrical field coupling, it could be a magnetic field coupling as well. Another question. Okay. Somebody did ask, what is the dot on the inductor? Why we put dot on the inductance? Well, we put a dot on the top of the inductance because this is the marking of the beginning of the winding of the inductance. Normally, inductance doesn't have a sense, doesn't have a direction like a diode or something. But we mark this inductance beginning point because this is when the wire is most closest to the core, and then we start the winding from inner core to the outside. This dot, it should be always looking to the switching node. Many times happen that your switching frequency is 200-300 kilohertz, but you hear from the DC-DC converter some high frequency noise during his switching. Normal human ear doesn't hear more like 16 kilohertz. A very, very good virtuous violinist can hear maybe that kind of frequency. I know there are some hi-fi freaks, they can hear 22 kilohertz, but I have a friend who is his doctor and tell me it's a childhood you have 16 kilohertz maybe when you're less than 2-3 years. After that is going away, but you can still hear not hundred of kilohertz, but it's still there. You can hear what is happening. If you take the inductor and turn 180 degree on the PCB, the noise is gone. Why? Maybe it was on the wrong direction because of the dot. That is very important also in terms of EMI. Sometimes I had really an issue when I saw the inductor in the wrong direction was much, much more higher amplitude in the EMC level when I turned 180 degree, and it was because the dot was not in the right direction. This is the only one why we are notify the dots for the inline chokes. Now, common mode chokes need to know that because you have to know the input of the common mode choke to be in phase to have the current compensation. But yeah, normally the normal inductor doesn't need. A rod core inductor doesn't have a dot. Make no sense because you can turn only if you turn 90 degree it will be different, but 180 degree will be no difference. Okay, let me check. Another question. Capacitance. Why is capacitance different at different voltage? Oh, yeah, this is a very good question. I like this question because many times I see designers which are using for a 12-volt application a 16-volt capacitor because they say, I have only 12 volt, why I should use more like 16 volt? Because the capacity is measured in laboratory condition maybe with only 1 volt. As soon you put 12 volt to this capacity, it won't have the value of the data sheet. it will be a DC bias. It will be a voltage drop. As soon you put a voltage drop to the capacity, his value, it will be goes down a lot. You can find all these values in the RedExpert. As soon you choose the capacity, you will see that is even a 50 volt capacitor with 1 microfarad. It depends on the package size. If you use a 0603, 0805, 1210 or 1812 side, the voltage dependency, it is crucial and very big. If you have space, don't use a 0603 capacitor, put 1210 because his voltage dependency, the capacity drop will be not that big like by 0603. This is, of course, you can avoid if you use a NP0 dielectric and you pay a lot of money for this capacitor. They are more stable in voltage, of course, but normally people doesn't want to pay too much for capacitor. I know that today many people are happy to have any kind of capacitor because it's an allocation type, but well, I would suggest anyhow look to this X7R, X5R on the voltage dependency. What about DC bias? Yes, this is what I'm talking about. The DC bias is the DC bias can be in two different areas. One is the DC bias which affect the saturation of the inductance, and the second DC bias is because of the voltage, it can affect the capacity in his parameter. All right, we are in time. I did not exceed the expected time, so 45 minutes was planned. If you have any other question, just please leave it in this chat and I will reply, of course, everything by email personally, which I did not respond right now. So I hope you enjoy it. And what I can tell you, the last things which about EMC, I can tell you, please never give up. There's always a solution. Maybe you don't see it right now, but if you call us, we have salespeople, the electronic engineer, we have field application engineer worldwide acting, more like 200 guys. We are worldwide acting for like field application engineers, and we try to give you an idea, a hint how it works. Why should use maybe this another component? It's like my chess speed, you know, when two people playing chess, the third guy is looking to the table and say, hey, why he do this movement? He doesn't see that this is not the right one. He will be going in the trap. So the same for us. Maybe our colleagues or sales guys, they are not so focused on your function, and he will say, hey, this is a wrong component. Don't use that. Maybe it's even a cheaper solution or even maybe another solution which fits on the same size. Please try to use these ones. If your design is in some other country, don't be afraid. You will get in all these red colored countries. I like especially Grönland. Why is colored? Because Grönland belongs to Denmark, and we have in Denmark salespeople. But Grönland, I don't saw any more. I did not saw really too much electronic designers there. But maybe there are some people hiding from electrosmoke. I don't know. But anyhow, you can have all these countries supplied by direct sales from Würth Elektronik. The yellow painted we have only just by using distributor, a big distributor like DigiKey, Mauser, or Farnell. It's always available. But if you want to have samples, you even then, if you're not in a red colored country, you can ask for samples. Samples will be supplied always free of charge. If you want to keep in touch with us, we have also a phone and ISOS email hotline. If you want to keep in touch with me, I have also a Twitter account. I have a YouTube channel on tvonline.com/YouTube. You will find some nice videos, which we did make short videos for different tutorials, like what means saturation current, what means the ESD shock. Especially look on the ESD shock, which I make with one of my colleagues from the marketing department. It's nice to see the face. Even it's very much censored because she was scared when I shot the ESD and she held in hand the PCB. That's so funny, you know. Sometimes we make some funny things as well in the laboratory, but most are professional made for explain what is happened with the inductor, what is happened with the capacitor, what is in the ferrite inside, and so on. If you keep in touch, LinkedIn or just follow by Twitter. I hope you enjoy it, and if you have any other question, just let us know. We will try to answer that within 24 hours. Thank you so much for your attention. Bye.